Hi, my name is Nasser. In this video we will discuss functions. Here is a quick overview of what we will cover in this video. First we will talk about the basic definition of a function. Then we will discuss the domain, codomain and range of a function. We will look at different types of functions which include onto function, one-to-one function and bijective function. Then we will discuss what is meant by the inverse of a function. We will see the definition of the composition of two functions. And finally, we will solve various problems related to functions. Let us see the definition of a function. A function from a set A to another set B is a rule or formula that maps each element of the set A to a unique element of the set B. A function is usually denoted by small letters f, g or h. A function f from a set A to another set B is denoted by this expression. The definition of a function has two important points: each element and unique element. The rule must provide mapping for each element of the set A. If there is an element in the set A for which there is no associated element in the set B, then the rule is not a function. It could be something else, but mathematically we do not call it a function if it does not provide mapping for each element of the set A. The second point is that each element of set A must be mapped to a unique element of the set B. Let me explain this with examples. We have two sets A and B. Set A has 3 elements and the set B has 5 elements. We have 4 different mappings. First, we will discuss which of the 4 mappings are not functions. The first mapping maps 1 to 1 and 2 to 12. You see that 3 is not mapped to any element of the set B. So, this mapping does not fall under the definition of a function. Therefore, this mapping is not a function. Let us look at the second mapping. 1 is mapped to 2 elements, 1 and 12. 2 is mapped to 4 and 3 is mapped to 17. Element 1 is mapped to 2 elements. This mapping violates the second condition of being a function. Again, this mapping also does not fall under the definition of a function. What about the last 2 mappings? Is each element of the set A mapped? Yes. Is each element mapped to a unique element? Yes. So the last 2 mappings are functions. Now let us see what is meant by the domain, codomain and the range of a function using this example. The set A is called the domain of the function. The set B is called the codomain of the function. In general, the range of a function is a subset of the codomain B. The range consists of the elements of the codomain which are associated with one or more elements of the domain. In this example, only the elements 1 and 12 are associated. Therefore, the range is equal to the set containing 1 and 12. Symbolically, we write f of 1 is equal to 12. The element 12 is called the image of 1 under the function f. F of 2 is also equal to 12, so 12 is also the image of 2 under the function f. And f of 3 is equal to 1. So 1 is the image of 3. Inverse image of an element. If f of A is equal to B, then A is called the inverse image of B. In this example, the inverse image of 1 is 3 and the inverse images of 12 are 1 and 2. What about the inverse images of the elements 4, 9 and 17? They do not exist. You see that the inverse images are not unique. An element can have 0 or any number of inverse images. The uniqueness or the existence of the inverse image of an element does not violate the definition of a function. However, we will see that we can categorize functions into different types based on the existence or uniqueness of the inverse images. Look at this function. you see that each of the elements of the codomain has at least one inverse image. In other words, the range is equal to the codomain. These types of functions in which the codomain is equal to the range are called onto functions. Let us see the formal definition of an onto function. A function is called an onto function if the range is equal to the codomain. In mathematical language, a function f from a set A to another set B is called an onto function if for all elements B in the codomain there exists an element A in the domain such that f of A is equal to B. This is just a mathematical way of saying that each of the elements in the codomain has at least one inverse image. This expression means for all elements in the codomain we have at least one element in the domain such that the element of the domain is an inverse image of the element of the codomain. Let us see another type of function. We have three sets A, B and C. We have a function f from A to B. We have another function with the same domain A and codomain B. We have two more functions from the set A to the set C. So we have four different functions f, g, h and k. The domain is the same for all the four functions. Domain is A. However, for these two functions the codomain is the set B, and for these two functions the codomain is the set C. Observe the number of inverse images for the first two functions. Each element of the codomains has 0 or 1 inverse image. Means that no element of the codomains has more than one inverse images. The inverse image of A is 2, the inverse image of B is 4, the inverse image of C is 1 and that of D is 3. So each of them has exactly one inverse image. In this function, each of the elements A, B, C and D have exactly one inverse image. However, the element E has no inverse image. Although the element E has no inverse image, we are only interested in the property that no element has two or more inverse images. In math language, we say that f of x is not equal to f of y if x is not equal to y. So this expression means if x and y are two different elements, then f of x and f of y are also different. The expression is the same for the function g as well. Now look at the functions h and k. The element A has two inverse images. Likewise for function k, element D has two inverse images. H of 2 is equal to H of 3 and k of 1 is equal to k of 4. Although 2 and 3 are two different elements, but their image is the same. A has two inverse images. Likewise, for the function k, D has two inverse images. The first two functions in which no element of the codomain has more than one inverse image are called one-to-one functions. Let us see the formal definition of a one-to-one function. A function f is called one-to-one if whenever f of x is equal to f of y, then x and y are the same element. This means that no two elements of the domain map to the same element of the codomain. F of x is equal to f of y implies equality of x and y. An equivalent contrapositive statement is that for all x and y in the domain, x is not equal to y implies that f of x is not equal to f of y. These two statements are equivalent. This is just a contrapositive way of saying the same statement. So this statement means whenever x and y are two different elements, then their images are also different. Now we will see third type of function. A function that is onto as well as one-to-one is called a bijective function. In a bijective function, each of the elements of the codomain has exactly one inverse image. Here is an example of a bijective function. Each of the elements A, B, C, and D of the codomain has exactly one inverse image. If we invert the direction of the arrows and the role of the domain and the codomain, the resulting function will also be a valid function because the inverse image for each element exists and is also unique. Suppose f is a bijective function from a set A to another set B. If we invert the role of the domain and the codomain, then this inverse mapping is called the inverse function of f. The inverse of a function is a valid function if and only if the underlying function is a bijective function. Let us see why the inverse mapping is not a valid function if the underlying function is not bijective. If f is not onto, then there will be an element for which the inverse image will not exist. This will violate the for each condition of the definition of a function. In this case, the inverse mapping will not be a valid function. If the given function is not 1 to 1, there will be an element for which the inverse image is not unique. This will violate the uniqueness condition of the definition of a function. So the inverse function exists if the given function is a bijective function. Composition of functions. If we have two functions f and g, f is a function from a set A to a set B and g is a function from the set B to a set C. We can apply the functions f and g in series. First apply the function f to an element of the set A and then apply the function g to f of A. The resulting element belongs to the set C. So this mapping in series can be considered as a single mapping from the set A to the set C. Please keep in mind that we cannot apply g and then apply f. The reason is that if we apply g to an element of the set B, then g of B belongs to set C. But the function f is defined only for the elements of the set A. We have an element in the set B. Suppose if we apply g on B, then the resulting element belongs to the set C because the function g is from set B to set C. Can we apply f on g of B? No. Why? Because g of B is an element of the set C and the function f is defined for the elements of the set A. Therefore, we cannot apply f to the elements of the set C. This is only possible if the domains and the codomains are the same set. Composition of g and f is denoted by this expression. G circle f of A is equal to g of f of A. Let us see the composition of functions graphically. We have three sets A, B, and C, and there is an element x of the set A. When we apply f to x, we get f of x, and f of x belongs to the set B. Then we apply g on the element of the set B, we get an element of the set C. If we consider it a single mapping, then x is mapped to the element of the set C. So this is called composition of functions. The composition of functions is from the set A to the set C. Now we will solve various problems related to functions. I upload new videos every week. Please subscribe my channel if you haven't already subscribed. We start with a simple example. We have a function f from the set of real numbers to the set of real numbers. The domain and the codomain are the same, and the formula of the function is f of x is equal to x plus 1. It is not difficult to show that f is a valid function. For each element x in the domain, there is a unique element in the codomain. Let us prove that f is a bijective function. A function is bijective if it is onto as well as 1 to 1, so we need to prove that f is onto as well as 1 to 1. Onto, and we will prove that f is also 1 to 1. Suppose y is some element of the codomain. we will show that there is an element x in the domain such that f of x is equal to y. Let's find out what is the corresponding x. F of x is equal to y, x plus 1 is equal to y, and from this we can find that x is equal to y minus 1. So this is the corresponding element in the domain such that f of x is equal to y. F of y minus 1 is equal to y. For example, if we have 5, then f of 4 is equal to 5. If we have 7, f of 6 is equal to 7. If we have minus 8, f of minus 9 is equal to minus 8. You see that for each element y in the codomain, there is a corresponding element x in the domain such that f of x is equal to y. So f is onto. Let's prove that f is 1 to 1. Suppose we have two elements x and y such that f of x is equal to f of y. This means that x plus 1 is equal to y plus 1. We can cancel out 1 from both sides and x is equal to y. It means that f of x is equal to f of y is only possible whenever x and y are the same element. This is what is the definition of a 1-to-1 function. Therefore, f is 1 to 1. Since f is onto as well as 1 to 1, therefore f is a bijective function. In this example, we have function from the set of real numbers to the set of real numbers, and the formula of the function is f of x is equal to x squared. Let us check if this function is onto and 1 to 1. Onto. Suppose y is an element of the codomain. Let us find the corresponding x in the domain if it exists such that f of x is equal to y. F of x is equal to x squared, so we have x squared equal to y. This means that x is equal to y under root. We need to make sure that x belongs to the set of real numbers. Does it belong to the set of real numbers for all elements y? The answer is no. If y is a positive real number, then under root y belongs to the set of real numbers. But if y is a negative real number, then y under root does not belong to the set of real numbers. This means that for negative real numbers in the codomain, there is no corresponding element in the domain. We can also observe from the definition of the function that the resulting element is a positive integer. However, the codomain is the set of real numbers. It means that the negative real numbers are not mapped. There is no corresponding element in the codomain for negative real numbers. It means that f is not onto. Is it 1 to 1? Suppose f of x is equal to f of y for some elements x and y. This means that x squared is equal to y squared, but from this equation we cannot infer the equality of x and y because x and y may be different but their squared may be the same. For example, we have x equal minus 2 and y equal 2. These are two different numbers. What about their square? Are they equal? Minus 2 square and 2 square. This is 4, this is also 4. It means that there can be two numbers in the domain which map to the same number in the codomain. For example, minus 2 and 2 map to the same number, 4. In general, a and minus a map to the same number, a squared. So f is neither 1 to 1 nor onto. In this example, domain and the codomain are two different sets. We have function from the set of real numbers to the set of integers. And the formula of the function is f of x is equal to floor of x. This is called a floor function. Floor of x is equal to the greatest integer less than or equal to x. For example, if we have 4.1, then floor of 4.1 is equal to 4. Floor of 5.9 is equal to 5. Floor of 0.9 is equal to 0. But for negative numbers, floor of minus 2.9 is equal to minus 3, not minus 2. Why? Look at the definition. It is the greatest integer less than or equal to x. If we suppose it is -2 instead of -3, then -2 is not less than -2.9. Is it? No. The greatest integer which is less than or equal to -2.9 is -3. Therefore, floor of -2.9 is -3, not -2. Likewise, floor of -6.8 is equal to -7. Let us plot the floor function in a Cartesian plane. We have x-axis, we have y-axis. If the number is between 0 and 1, then that number is mapped to 0. Floor of all these numbers is equal to 0. If the number is less than 2 but greater than or equal to 1, then floor of all these numbers is equal to 1. If we have a number which is greater than or equal to 2 but less than 3, then floor of all those numbers is equal to 2. And like if the number lies between 3 and 4, their floor is equal to 3, and between 4 and 5, the floor of those numbers is equal to 4. On the negative side, if the number is between -1 and 0, if it is greater than or equal to -1 but less than 0, then the floor of all these numbers is equal to -1. If the numbers are between -2 and -1, floor of these numbers is -2. Between -3 and -2, floor of these numbers is -3. And between -3 and -4, the floor function is -4. So this is how a floor function looks like on a Cartesian plane. It's like a staircase. It is not difficult to show that f is a valid function. That is, each element of the domain has a unique image in the codomain. Let us check if f is an onto function. Suppose an element n belongs to the set of integers. This implies that n plus 0.5 belongs to the set of real numbers, the domain, and f of n plus 0.5 is equal to floor of n plus 0.5. This is equal to the greatest integer which is less than or equal to this number. The greatest integer less than or equal to n plus 0.5 is n. It means that for each element n in the codomain, there is a corresponding element in the domain such that f of n plus 0.5 is equal to n. So each of the element of the codomain has an inverse image. The range is equal to the codomain. F is an onto function. Is f 1 to 1? From the graph we can see that f is not 1 to 1 because the numbers between two consecutive integers map to the same integer. It means that the same number has multiple inverse images. So f is not 1 to 1. We just need to prove the existence of two different numbers which map to the same integer in the codomain. F of 4.1 is equal to 4. F of 4.2 is equal to 4. So I think that is sufficient to prove that f is not 1 to 1. In this example, we will find inverse of a function. We have f of x equal x cubed plus 5, where f is a function from the set of real numbers to the set of real numbers. Suppose f of x is equal to y. We have y equal x cubed plus 5. To find the inverse, we will find the value of x. This implies that y minus 5 equal to x cubed, and from this we can find the value of x. Y minus 5 raised to power 1 by 3 equal to x. So the inverse function g from the set of real numbers to the set of real numbers is g of y equal to y minus 5 raised to power 1 by 3. In this example, we will find composition of two functions. We have two functions with the same domain and the codomain. F of x is equal to x squared plus 1. Whereas g of x is equal to x plus 1 divided by 2. Let's find the composition of f and g. This is equal to g of x square plus 1, and this is equal to x square plus 1 divided by 2. And the final result, the composition of g and f is equal to x square divided by 2 plus 1. So composition of g and f is equal to x square divided by 2 plus 1. Let's check it. We have a number 3, x equal 3. F of 3 is equal to 3 square plus 1, which is equal to 10, and g of f of 3 is equal to g of 10 is equal to 10 plus 1 divided by 2. This is equal to 5.5. Now let us substitute x equal to 3 directly in the formula of the composition function. G circle f of x is equal to, here x is equal to 3. We have 3 square divided by 2 plus 1. This is equal to 9 by 2 plus 1. 9 by 2 is equal to 4.5 plus 1. This is equal to 5.5. We can find composition of two functions like this. This was our last example. We stop here. If you haven't subscribed my channel, please subscribe now and hit the bell icon so that you can receive a notification when I upload new videos. Thanks for watching.